everyone, my name is Hayman Aziz. This is on upper limit of coefficient or variation of data, which is part 2. We have already done part 1 in another video in which shortly I will show to you maybe some brief explanation. And secondly here, this is like a lecture note rather than just a video, so it may be a good idea if you would like to understand this theorem here or this concept in more depth. It may be a good idea if you practice or maybe do some of those examples in which given here by yourself. Summary of the first previous video. Then in the first video here, we analyzed, for example, here the behavior and upper limit value of the coefficient of variation, which we assumed it as a new statistical property of data. And especially here, it's limiting behavior. Then some new interesting results were produced in that video here, and this is the link. Then I advise if you can just look at this, then gives you a bit more help in deepening to this video. Now, the aim of this part, which is part 2 here, this is to analyzing for a wide range of probability distributions, and even including special and not just probability distribution. It means practically here, if you look at it mathematically, this can also be extended as a new dimension on the properties of function, practically. And then some of these interesting probability distributions are studied here. And then lastly here, which is the main goal of this video, constructing a general theorem or a principle that can lay out this idea. These are two functions in which we have, okay, they look like the probability distribution, then we study them shortly. And then on the top of that, we will have some special distributions. Now, this is the first one. This looks like exponential, but is not quite because this is multiplied by x. And then definitely here, if x is defined within this domain, k can be found within this value here, given that the conservation of probability satisfies. Then fairly is easy finding the mean of the distribution. Okay, although I haven't shown that integration, but I'm positive you can solve that integration by yourself. And secondly, the variance of the distribution. And then if, for example, beta approaches infinite, then the upper limit of this coefficient will be equal to 1 over root 2. In this case, it's fairly easy because we haven't got problem with finding mu, the mean, separately and finding the variance of standard deviation separately. So it means here this is quite straightforward. But the second example is different because firstly here, for example, if you calculate this, this is going to be the value of k, given that in terms of beta certainly, given that if this is assumed as probability distribution and the integration is equal to 1. But in here, mu, the mean depends on beta, because we can't just easily take beta infinite in this expression here, because you will get an indefinite value. And the same idea for variance of the distribution in terms of beta, in which this is slightly a more complicated expression, but you can work it out and reproduce it. There is a very, very interesting result here. Then if you notice that according to the definition of the coefficient of variation, what I did here, you can use a computer here to calculate this. Then I did it on the maximum ability of this normal computer in which it can do the calculation of This expression, when b is in the order of 10 to power 150, then c v, which is this value of the interest here, to 32 decimal places here, stopped here. But it doesn't mean that this is certainly here the maximum value, but at least this is the maximum value for this order. Then there is some interesting theorem. This idea of the theorem is quite useful in understanding this concept, which is fairly easy. I haven't shown the proof of those, okay, because the proof of those may require their own videos. For instance, here, if you have got an integration of a function between alpha and beta, and if this is approaching infinite, then certainly here, if you take the first moment, usually this is defined as moment of the function. If n is a positive number, then the second moment, then the third moment, all of those are approaching infinite, so cannot be defined. But if you have got a function between alpha and beta, if the value of this integration is defined, which is less than infinite, then not necessarily this is defined, or maybe the higher orders of the moment is defined. It can be both ways. It can be defined, which has got finite value, or maybe not defined, it has got infinite value. We have got few examples here. For example, now if I take this simple function, then obviously here the integration from 1 to infinite, then it means in this case alpha is 1 and beta is infinite. And then this tends to approach infinity. And the same can be applied if you take the first moment or the second moment. You can easily calculate those. But if I have got this function here, which is 1 over x squared, then if I integrate this between 1 to infinity, then I notice that the value of this calculation here is finite, but certainly here, if you calculate the first moment or the second moment or higher moment, then you will get all of them as infinity, not defined. If I have got this function here, maybe this is another example, but I have got the fourth function, which is quite strange. If, for example, here I take the integration of this between 0 and infinite, and if it comes out to be pi, it comes out to be pi over 2, which is a definite value. But if you calculate the first moment, or the second moment, or the third moment, and so on, surprisingly here, these values are neither infinite or nor even definite. They cannot be defined. The reason is clear, because sign of infinity, we do not know if this is -1, if this is 0.2, if this is +1, and so on. Although in this discussion here, we are excluding these types of functions to deal with. Now, why the above theorem is useful or discussed here? There are some key points. Firstly, here, for example, expectation and variance, asymptotic behavior, are directly linked to the integration of the distribution. This is, again, here another fact. But do not forget, it means if you expand this discussion here beyond this variable here in which we have, then still can be applied, because you can just define it regardless of statistics. So you don't need to mention expectation or variance here. The second point here is there are a number of expressions. Once you take the limits of the variable, maybe if you do not take care of the way in which you take the limit, you will get different results. For example, here, like this expression is a very simple example. If you just take the limit of n to infinity here, you notice that you will get an expression infinity divided by infinity, which is not defined. Okay. But if, for example, here you divide both numerator and denominator by n, and then simplify, then you will get 5/4. Then now, even if you take the limit, because 2/n will become 0 and 7/n becomes 0, then the limit of this will approach 5/4. This is not the only expression in which we have creating this trouble. Then it means it can be infinity minus infinity, 0 divided by 0, 1 to power infinity, or 0 times infinity. And the answer is easy, because whenever we talk about the infinity, this infinity is not the same as that infinity, or this infinity is not the same as that infinity. Infinity is just maybe a representation in which we tell a number is very, very large. But very, very large is relative large with respect to groups of dimension of other numbers. Now, some special functions and distributions are discussed here. The very first one, which is Poisson distribution. This is a discrete distribution, which is well known. Okay, and then if, for example, here beta approaches infinite, what I did here, I didn't write it in a normal conventional way in which from 0 to infinite, and then I did write it from 0, 1, 2, this is integer x, taking all of those integers, and then when b approaches infinite, so that you can analyze and then you find out that the asymptotic behavior of the coefficient of variation will become 1/√mu, where mu is the parameter of your distribution. Some analysis. So it means to understand this concept a bit more in depth, just assume b less than infinity. So for example, like 5, 10, whatever you want. Then the probability distribution has now to be redefined with a k, because that k will no longer be equal to 1, because you have got now 0 until 5. Then from the principle of conservation of probability, you can work out this k. Once you can work out this k, certainly the first moment of this distribution, the second moment of this distribution, the mean, the standard deviation can all be found. Then if you work it out, then you easily notice that it's going to be less than this 1/√mu. And this is a second distribution, which is a continuous distribution, well known as exponential. Okay, in this exponential here, and by the way, this exponential just as a reference, all of its moment, even if you take b the limit to infinity here, all become the finite value for all n positive integers. Some analysis here, we can assume beta equals a finite value like 5, like 10, whatever you want. And then the probability density function can now be rewritten as this, but this k is no longer equal to mu. We need to calculate it from the principle of conservation of probability. And then once you find this, then definitely here the density function is defined. And then you can find the first moment, the second moment, the mean and variance, the standard deviation. You notice that it comes out to be less than 1. Now, another distribution, which is called chi-square distribution. This chi-square distribution slightly is a bit more complicated than the others. Okay, but we are not going to deal with the integration part here, just try to understand the concept. We assume the same idea here, beta, but if beta approaching infinity here, then the behavior or the limit of the coefficient of variation becomes equal to this. Then this gamma is a gamma function. Again, here you don't need to worry about this function. So it means this has got its own expression, which is not relevant here to discuss. Some analysis. If I assume beta, like the other examples, maybe 5, maybe 10, then now certainly the probability density function would have now to be redefined, rewritten, but with a value of k. and this k from the conservation of the probability, which is equal to 1, can be calculated. But bear in mind, maybe this integration for certain values of lambda, which is the degree of freedom, may not be easily calculated analytically. Then you can use numerical methods. Then you notice that certainly the limit, or not the limit, the value of the coefficient of variation will be less than this value. Now, some conclusion and results of this idea here. So I presented this in more or less a mathematical way here, because this can also be extended to maths, not just statistics. So if I have got a function which is defined in this domain, and then if, for example, the limit of this function when x approaches infinite is a definite value, and if the integration of this function when beta approaches infinite is also a definite value, then the upper limit of the coefficient of variation will be the limit of the coefficient of variation when beta approaches infinite, and it is a finite value. This is the upper value, and this is normally the expression for your coefficient of variation. Then it means if you take the limit here, you will get an upper value. Now, there are few important points here. For instance, here now, you need to note that it can be possible, for example, the numerator and the denominator independently or separately approaching infinity, or even maybe approaching zero. But certainly here the defining of this will go back to the previous discussion in which we had, means you need to do some other calculation to make the expression meaningful. The last point here is, there is an interesting question. Is that the only function in which we have where it has got this property? Or there are some other functions in which they are dependent on different orders of the moment of the function? We do not know yet. I haven't analyzed it myself, and as far as I'm aware, I don't think there is any such study in that area here. Hoping you have enjoyed it and useful for you. Any comments, any points in which you have, this is my email. Please contact me. Thanks for watching.